Hello everyone, my name is Abhiraj Chouhan and I am a student of MTech-IT 4th semester. Today I am solving the question paper of Internal 2 for my Numerical Analysis and Design assignment. So let's begin. Let's start with question number 1, which asks us to write an algorithm for Newton's forward difference interpolation formula. This method is used to interpolate a function value at a point using a set of equally spaced data points. The algorithm begins by taking input a set of n plus 1 points where xi are equally spaced with the step size of h and the point x where we want to evaluate the function. We first compute the forward differences, the second, and so on, up to the nth difference. These differences form a difference table. Next, we calculate the normalized distance where x0 is the starting point, and then we apply Newton's forward difference formula up to the nth term. Each term involves a binomial coefficient multiplied by the kth forward difference. The algorithm iteratively computes this sum to approximate the function value at x. This method is particularly useful when the data points are equally spaced, such as in time series analysis. Here we have written the algorithm as you can see. So let's move to the next question. Moving to question number 2, we need to write Python code for Newton divided difference interpolation formula, which is more flexible than the forward difference method because it works for unequally spaced points. The code takes a list of points x, I, y, I and target points x as input. It first builds a divided difference table with the zero divided difference. The first is f x I plus 1 is equals to y I plus 1 y I x divided by x I plus 1. The second is f I plus 1 x I plus 2, and then so on. Then it uses the formula px is equals to fx0 plus fx0 x1 x minus x0 plus fx0 x1 x2 x minus x into x minus x 1 plus plus continuing the formula, computing the system iteratively. This code efficiently computes the interpolated value and can handle any sets of points. For example, data point 0, 1, 1, 3, 2, 5, and 4, 7. The interpolated value at x is equals to 0 is approximately 6, which aligns with the expected polynomial behavior. Here you can see the code written for the Python for the Newton divided difference interpolation formula. You can see it. Now moving to the next question. Question 3 asks us to prove that the sum of Lagrange interpolation coefficient is 1. Lagrange interpolation expresses a polynomial px that passes through points xi, yi as px where Lix is the Lagrange basis polynomial. Li polynomial to prove the sum of coefficients equals 1. Consider the polynomial px is equals to 1 a constant function. Since px is equals to 1 passes through all points, we can write it using Lagrange interpolation. This holds because the Lagrange basis polynomials are conducted to satisfy Lix j is equals to 1 if j I is equals to j and 0. Otherwise, ensuring the interpolation is exact for polynomial degree at most n. This property is fundamental to Lagrange interpolation, guaranteeing that the basis polynomials of the form a partition of unity. It is a key reason why Lagrange interpolation is so effective for polynomial fitting. Moving to our next question, question number 4. Question number 4 asks us to derive Simpson's 3/8 rule from the general quadrature formula. The general quadrature formula approximates the integral of fx from a to b using polynomial that n degree n that passes through n plus 1 points. For Simpson's 3/8 rule, we use a cubic polynomial degree 3 over 4 equally spaced points x0, x1, x2, and x3, where xi is equals to a plus I to the power I into h and h is equals to b minus a by 3. We approximate we approximate the integral of a to the power b fx dx by integrating the cubic polynomial px that interpolates fx at these points. Using Newton's Cotes quadrature, we compute the weights by integrating the Lagrange basis polynomial for 4 points. The interval a b is split into three subintervals, so h is equals to b minus a by 3. The formula becomes integrate of a to the power b fx dx is equals to 3h by 8 3h by 8 f 3 3h by 8 into fx0 plus 3 fx1 plus 3 fx2 plus f3 plus fx3. To derive this, we integrate each Lagrange basis polynomial polynomial Lix over AB. After computing the integrals which I have detailed in my slides, the weights simplify 1, 3, 3, 1, and the factor 3h8 comes to the normalization over the interval. This gives a Simpson's 3-8 rule, which is more accurate than the one-third rule for certain functions because it uses a higher degree polynomial. Here you can see the full derivation of the Simpson's 3-8 rule. Moving to our next question. Question number 5 asks us to obtain Simpson rule from Newton Cotes formula. Typically, Simpson rule refers to the one-third rule, which uses a quadratic polynomial over 3 points x0, x1, x2 with h is equals to b minus a by 2. The Newton Cotes the Newton Cotes formula approximates the integral of a to the power b fx by integrating a polynomial that passes through the given points. For 3 points, we fit a quadratic formula becomes integration of a to the power b fx dx approximation to h by 3 into fx0 plus 4 fx1 plus fx2. This is Simpson's one-third rule, widely used for numerical integration due to its simplicity and accuracy for smooth function. The derivation involves computing integrals of the basis polynomial. Interestingly, if the question in, intended the 3/8 rule, we covered that in the previous question. It is a natural extension using 4 points instead of three. The Newton Cotes framework is versatile and can derive many quadrature like this. Here we have here we have derived the Simpson rule from the Newton Cotes formula. You can see. To wrap up, we have explored key numerical analysis technique. Today, we have developed an algorithm for Newton forward difference interpolation and implemented Newton's divided difference for interpolation in Python. We proved that the Lagrange coefficient sums to one fundamental property of interpolation. Finally, we derived Simpson's 3/8 rule and the one-third rule using general quadrature and Newton Cotes formula, showcasing their utility in numerical integration. These methods are crucial for application in engineering, physics, and data science, where approximation and integration are common tasks. I hope my solution were clear and thank you for watching this video.